Look up on a clear night, away from city lights, and you will see a few thousand stars scattered across the darkness. Pinpoints of light, some bright, some faint, some steady, others flickering gently in the air above you. It's beautiful, it's humbling, and it's misleading. What you are seeing is not the universe as it exists right now. You are seeing it as it once was. The light reaching your eyes tonight began its journey years ago, decades ago, sometimes centuries ago. Even the nearest stars are already outdated by the time their light arrives. Space does not offer live images, it offers history. Every glance upward is a glimpse into the past. Now imagine looking not years into the past, but billions. Imagine seeing light that began its journey when the universe itself was young, when the first stars were only just beginning to ignite, when galaxies were not yet the vast, ordered structures we see today, but fragile experiments of gravity and gas, still uncertain of their shape. For most of human history, this was impossible. Our eyes could only collect light from nearby space. Even our best telescopes struggled as distance increased. The farther we tried to look, the blurrier the universe became. The early cosmos remained hidden, sealed away behind the limitations of our instruments. Its secrets existed beyond reach, beyond resolution, beyond confirmation, until we built something specifically to look for it. The James Webb Space Telescope launched on Christmas Day, 2021. It was the most ambitious space observatory ever constructed, designed not to study familiar stars or nearby galaxies, but to see what no human instrument had ever seen before. Webb was built to look backward in time, deeper than any telescope before it. It does not observe the universe the way our eyes do. Webb sees in infrared light, wavelengths stretched longer and longer as space itself expands. Light that began its journey billions of years ago arrives faint and reddened, carrying information from the universe's earliest chapters. Webb was designed to capture those ancient photons, to see through cosmic dust, through distance, through time itself. Its mission was simple: confirm what we thought we already understood. According to modern cosmology, the universe began 13.8 billion years ago in an event we call the Big Bang. In its earliest moments, the universe was unimaginably hot and dense. Matter and energy were so tightly packed that light could not travel freely. Space was filled with an opaque fog of particles and radiation. For hundreds of thousands of years, the universe remained dark. Then it cooled. As temperatures dropped, electrons and protons combined to form hydrogen atoms. Space became transparent. Light was finally able to travel unhindered. This moment, known as recombination, released a faint afterglow that still fills the universe today, the cosmic microwave background. After that came a long silence. No stars existed yet, no galaxies. Only vast clouds of hydrogen and helium drifting outward as space expanded. Astronomers call this period the cosmic dark ages. Gravity worked slowly, patiently, pulling slightly denser regions inward. Tiny fluctuations in density, barely visible in the cosmic microwave background, began to grow. Eventually, those regions collapsed far enough for the first stars to ignite. These first stars were unlike those we see today. They were massive, short-lived, and violent. They burned through their fuel quickly and died in powerful supernova explosions, scattering heavier elements like carbon, oxygen, and iron into space. Only after these early stars lived and died could later generations form, stars capable of building planets, chemistry, and complexity. Based on decades of observation and theoretical modeling, Astronomers assembled a timeline for this process. The cosmic microwave background formed roughly 380,000 years after the Big Bang. The first stars appeared somewhere between 100 million and 200 million years later. Small, chaotic proto-galaxies formed from clusters of these early stars, merging and growing over hundreds of millions of years. Galaxy formation, according to everything we knew, was slow, messy, incremental. Computer simulations supported this picture. Observations from earlier telescopes like Hubble reinforced it. Everything pointed toward a universe that took its time assembling structure. By the standards of cosmology, the timeline seemed well understood. James Webb was built to test this picture directly. Its mirrors, coated in gold to reflect infrared light, would capture photons that had been traveling for more than 13 billion years. It would see galaxies as they existed just a few hundred million years after the Big Bang, during the critical era when structure was supposedly just beginning to form. Scientists expected to see small, irregular galaxies, dim collections of stars, proto-galaxies still collapsing, still merging, still finding their shape. They expected confirmation. What they received instead was surprise. In July 2022, Webb released its first deep field image. It showed a patch of sky no larger than a grain of sand held at arm's length, a region that appeared empty to previous telescopes. Inside that tiny patch were thousands of galaxies. Some were nearby, cosmically speaking. Others were unimaginably distant. Their light had been stretched by billions of years of cosmic expansion, arriving faint and red at Webb's detectors. Astronomers immediately began analyzing the most distant ones, measuring their redshifts to determine how early in cosmic history they existed. Redshift is a measure of how much the universe has expanded since light left a galaxy. The higher the redshift, the farther back in time we are looking, and that is where the problem appeared. The galaxies from the early universe were not small. They were not chaotic. They were not primitive. They were large. They were bright. Some displayed clear spiral arms, elegant curves of stars rotating around dense central regions. Others showed distinct bulges surrounded by rotating disks. These were not fragile, newly formed systems. They were mature. Some of these galaxies existed just 300 million years after the Big Bang, others at 400 million, 500 million. According to our models, this was barely enough time for the first stars to form at all, let alone to live, die, enrich their surroundings with heavy elements, and assemble into galaxies containing hundreds of millions or even billions of stars. Yet the evidence was there. The light from these galaxies showed spectral signatures of heavy elements, elements that could only have been forged in the cores of earlier generations of stars. These galaxies had histories. They had already lived through cycles of star formation and death. They looked old. Astronomers checked their measurements. They recalculated redshifts. They searched for errors. Dust can make galaxies appear brighter and therefore closer or more massive than they truly are. Gravitational lensing can magnify distant objects, distorting our perception. Some cases were explained by these effects. Many were not. The galaxies remained massive, structured, ancient. This created a tension at the heart of cosmology. Either our instruments were misleading us, or our understanding of galaxy formation was incomplete. Either something unknown was accelerating star formation in the early universe, or the timeline we had trusted for decades needed revision. Neither possibility was comfortable. Some researchers proposed modifications to existing models. Perhaps stars formed more efficiently in the early universe. Perhaps dark matter behaved differently. Others suggested we were misinterpreting the data. that follow-up observations would resolve the discrepancies. But beneath the technical debates, a quieter realization emerged. The universe had surprised us again. We had built a telescope to confirm what we thought we knew. Instead, it showed us something that did not fit, something that arrived too early, something that formed too fast. The cosmos, as always, proved more complex than our models, more subtle than our expectations, and more willing to challenge our assumptions. To understand why these galaxies pose such a problem, we must trace the origin of the timeline itself, the story of how we learned when the universe began, and how we came to believe it unfolded the way it did. Only then can we understand why seeing galaxies that formed too soon unsettles everything we thought we knew about cosmic history. The story of how we determined the age of the universe begins, oddly enough, with a debate about whether the universe had an age at all. In the early 20th century, most astronomers believed the cosmos was eternal and unchanging. Galaxies existed in a static arrangement, neither expanding nor contracting, suspended in a timeless equilibrium. This seemed intuitive. The night sky looked the same as it had for thousands of years of recorded human history. Stars were born and died, but the overall structure remained constant. The universe simply was, with no beginning and no end. Albert Einstein's equations of general relativity, published in 1917, actually predicted that the universe should either be expanding or contracting. A static universe was unstable, according to the mathematics. But Einstein, like most scientists of his time, believed in a static cosmos. He modified his equations, adding what he called the cosmological constant, a kind of anti-gravity force that would hold the universe in place. It was an elegant mathematical fix to a problem that seemed more philosophical than physical. Then came the observations that changed everything. In the 1920s, an astronomer named Edwin Hubble was working at the Mount Wilson Observatory in California, using what was then the world's largest telescope. He was studying fuzzy patches of light called nebula, trying to determine whether they were clouds within our own galaxy or separate galaxies beyond it. By identifying specific types of variable stars in these nebulae, stars whose brightness oscillated in predictable patterns, he could calculate their distance. What he found was astonishing. These nebulae were millions of light years away, far beyond the boundaries of the Milky Way. They were galaxies in their own right, island universes scattered through space. But Hubble noticed something else, something even more profound. When he analyzed the light from these distant galaxies, he found that their spectral lines were shifted towards the red end of the spectrum. This redshift indicated the galaxies were moving away from us. And the farther away a galaxy was, the faster it appeared to be receding. This relationship, now called Hubble's law, suggested something remarkable. The universe itself was expanding. Space was stretching, carrying galaxies along with it. If the universe is expanding now, it must have been smaller in the past, denser, hotter. Run the clock backward far enough, and you arrive at a moment when all the matter and energy in the cosmos was compressed into an infinitesimally small point. This was the insight that led to what we now call the Big Bang Theory. The universe had a beginning. It had an age. And if we could measure the rate of expansion accurately enough, we could calculate when that beginning occurred. For decades, determining the exact age of the universe remained challenging. Measuring distances to faraway galaxies was difficult. Different methods gave different results. Estimates ranged wildly, from 10 billion years to 20 billion years. But astronomers kept refining their techniques, building better instruments, gathering more data. Slowly, the uncertainty narrowed. Then, in 1965, two researchers at Bell Labs made an accidental discovery that would transform cosmology. Arno Penzias and Robert Wilson were testing a sensitive radio antenna, trying to eliminate sources of background noise. They found a persistent hiss coming from every direction in the sky, a faint microwave radiation they couldn't explain. After ruling out all possible terrestrial sources, including famously pigeon droppings on the antenna, they realized they'd detected something cosmic. This was the afterglow of the Big Bang itself, the cosmic microwave background radiation that fills all of space. The discovery of the cosmic microwave background provided powerful confirmation of the Big Bang theory, but it also presented a puzzle. The radiation was remarkably uniform, almost exactly the same temperature in every direction. This uniformity was difficult to explain. Different regions of the early universe, separated by vast distances, should never have been in contact with each other. They couldn't have exchanged energy or reached the same temperature. Yet the cosmic microwave background showed they had. How? The answer came in the form of inflation theory, proposed in the early 1980s. According to this idea, the universe underwent a brief period of exponential expansion in its first fraction of a second, growing faster than the speed of light. This rapid inflation smoothed out any initial irregularities, explaining the uniformity of the cosmic microwave background. It also predicted that tiny quantum fluctuations during inflation would be stretched to cosmic scales, creating the slight variations in density that eventually became galaxies and galaxy clusters. When satellites measured the cosmic microwave background in detail, they found exactly the pattern of tiny fluctuations inflation theory predicted. Throughout the 1990s and 2000s, increasingly sophisticated space missions mapped the cosmic microwave background with extraordinary precision. The Cosmic Background Explorer satellite, launched in 1989, confirmed the radiation's blackbody spectrum and detected the predicted tiny temperature variations. The Wilkinson Microwave Anisotropy Probe, launched in 2001, measured these variations across the entire sky, allowing astronomers to determine the universe's composition and geometry with unprecedented accuracy. The Planck satellite, launched in 2009, pushed measurements even further, creating the most detailed map of the ancient universe we've ever produced. These missions did more than just map the cosmic microwave background. They allowed scientists to calculate fundamental parameters of cosmology with remarkable precision. The age of the universe, its rate of expansion, the relative amounts of ordinary matter, dark matter, and dark energy. By analyzing the patterns in the cosmic microwave background, astronomers could determine that the universe began 13.8 billion years ago, give or take a few tens of millions of years. This wasn't a rough estimate anymore. It was a precise measurement, backed by multiple independent lines of evidence. With the age of the universe established, cosmologists could build detailed computer simulations of how structure formed over cosmic time. They could model how the tiny density fluctuations in the early universe grew under gravity, how dark matter clumped together first, forming scaffolding for ordinary matter to follow. They could simulate the formation of the first stars, the assembly of the first galaxies, the gradual construction of the cosmic web we observe today. These simulations incorporated known physics, the behavior of gravity and gas dynamics, and star formation. They required enormous computational power, but they produced results that matched observations of the nearby universe remarkably well. According to these simulations, the first stars ignited roughly 100 million to 200 million years after the Big Bang. The first small proto-galaxies assembled over the next few 100 million years, gradually merging and growing. By about 1 billion years after the Big Bang, the first relatively large galaxies should have appeared, but they would still be messy and irregular compared to modern galaxies. Mature spiral galaxies with well-defined disks and spiral arms wouldn't emerge until several billion years had passed. This timeline made sense. It fit with what we understood about star formation, galaxy assembly, and the growth of cosmic structure. James Webb was designed specifically to observe this early epoch, to see the first galaxies forming and confirm the predictions of these sophisticated models. Its infrared vision would pierce through cosmic time to the era when the universe was just a few 100 million years old. Scientists expected to see small, irregular proto-galaxies, perhaps a few primitive structures just beginning to organize. They expected the observations to validate decades of theoretical work. With this timeline established, astronomers trained James Webb on the deepest reaches of space, expecting confirmation. But the universe had other plans. The James Webb Space Telescope sees the universe differently than any instrument before it. Where Hubble captured visible light, the same wavelengths our eyes detect, Webb looks at infrared radiation. This might seem like a minor technical detail, but it changes everything. Infrared light can pass through cosmic dust that would block visible light entirely. More importantly, the expansion of the universe stretches light from distant galaxies, shifting it from visible wavelengths into the infrared. The farther away a galaxy is, the more its light is redshifted. To see the earliest galaxies, the ones formed when the universe was young, you need to look in infrared. Webb was built precisely for this purpose. Its primary mirror is enormous, 6.5 meters across, composed of 18 hexagonal segments coated in a microscopically thin layer of gold. Gold reflects infrared light efficiently, making it the ideal choice despite the cost. The telescope operates at incredibly cold temperatures, cooled by a tennis court-sized sunshield that blocks heat from the sun, Earth, and Moon simultaneously. This cooling is essential. If the telescope itself were warm, its own infrared radiation would overwhelm the faint signals from distant galaxies. At its operating temperature, just a few dozen degrees above absolute zero, Webb can detect the faintest whispers of light from the edge of the observable universe. The first deep field image, released in July 2022, targeted a region called SMACS 0723. It's a galaxy cluster, and its immense gravity bends space around it, acting like a cosmic magnifying glass. This gravitational lensing amplifies light from galaxies far behind the cluster, making them bright enough for Webb to detect. The image shows thousands of galaxies, stretched and distorted into arcs and smears by the warped space. Some of these galaxies are relatively nearby. Others are among the most distant objects ever observed. Astronomers immediately began analyzing the light from these galaxies to determine their redshift. Redshift is measured as a number, labeled with the letter Z. A galaxy with redshift Z equals 1 appears as it was roughly 8 billion years ago. Higher numbers mean greater distances and earlier times. Galaxies with redshift above 10 existed when the universe was less than 500 million years old. Before Webb, only a handful of galaxies had been confirmed at such extreme distances. Webb found them routinely. One of the first candidates to capture attention was designated Glass Z13. The name indicates it was discovered in a survey program and has an estimated redshift around 13. If accurate, this galaxy existed just 300 million years after the Big Bang. That alone would be remarkable. But what shocked astronomers was the galaxy's appearance. It wasn't a small, irregular smudge. It showed structure. It appeared to contain a substantial population of stars, far more than early models predicted should exist at that time. Another candidate, found in data from the Cosmic Evolution Early Release Science Survey, was initially estimated to have a redshift above 16, which would place it at just 250 million years after the Big Bang. Follow-up observations later suggested this might be an overestimate, possibly caused by unusual properties of the galaxy's light. But even revised estimates placed it extraordinarily early in cosmic history. And it wasn't alone. As Webb collected more data, more distant galaxy candidates emerged. CEER S93316. Multiple objects in the extended growth strip. Galaxies scattered across different patches of sky, all showing similar characteristics. They were bright. They were massive. They had structure. Some displayed hints of spiral arms, features that shouldn't exist in such young galaxies. Others showed evidence of stellar populations that had already undergone significant evolution, with multiple generations of stars having formed and died. The mass of these galaxies became a central point of concern. Astronomers estimate galactic mass by measuring the total light output and using models of stellar evolution to determine how many stars would be needed to produce that much light. Several of Webb's early galaxy candidates appeared to contain hundreds of millions of solar masses worth of stars. Some estimates suggested billions. To put this in perspective, our own Milky Way contains several 100 billion stars and took billions of years to assemble. These early galaxies, existing when the universe was less than 5% of its current age, already contained a significant fraction of that mass. The problem wasn't just individual galaxies, it was the population statistics. When you observe a patch of sky, you're seeing a representative sample of the universe at that distance. If you find one massive galaxy at high redshift, you might explain it as a statistical outlier, an unusually dense region that collapsed earlier than average. But Webb was finding numerous massive galaxies at these extreme distances. This suggested that massive galaxy formation in the early universe wasn't rare. It was common. The models hadn't predicted this. Then there was the question of structure. Modern galaxies come in distinct types. Elliptical galaxies are smooth and featureless, containing primarily old stars in random orbits. Spiral galaxies have rotating disks with elegant spiral arms, sites of ongoing star formation. Irregular galaxies lack clear structure, often the result of gravitational interactions or mergers. According to standard theory, early galaxies should almost all be irregular. They're still assembling, still experiencing frequent collisions and mergers. Organized structures like spiral arms require time to develop and stabilize. Yet some of Webb's high redshift galaxies showed surprisingly regular morphologies. Clear disk structures, central bulges surrounded by extended stellar distributions. Features that suggested rotational dynamics, not chaotic random motion. These weren't the messy proto-galaxies the models predicted. They looked like scaled-down versions of galaxies in the modern universe, just existing billions of years earlier than they should. Spectroscopy provided another layer of complexity. When you spread a galaxy's light into a spectrum, you can identify specific absorption and emission lines created by different elements. The pattern of these lines tells you what the galaxy is made of. Early galaxies should be composed almost entirely of hydrogen and helium, the only elements created in the Big Bang. Heavier elements like carbon, nitrogen, oxygen, and iron are forged inside stars and scattered into space when those stars die. It takes time for these elements to accumulate. Multiple generations of stars must form, live, and die before significant heavy element enrichment occurs. Some of Webb's distant galaxies showed spectral signatures indicating the presence of heavy elements. Not in huge quantities, but enough to suggest that multiple stellar generations had already occurred. Stars had formed, burned through their nuclear fuel, exploded as supernovae, and seeded the interstellar medium with their synthesized elements. This entire cycle had completed, possibly multiple times, within the first few 100 million years of cosmic history. The statistical significance of these observations grew as more data accumulated. Early results could be dismissed as flukes, measurement errors, or misidentified objects. But as Webb continued observing, the pattern held. Different teams using different analysis methods on different patches of sky were finding similar results. The early universe was producing massive, structured galaxies at a rate and on a timescale that existing models couldn't easily explain. Astronomers began proposing various explanations. Perhaps the mass estimates were wrong, inflated by unusual dust properties or gravitational lensing effects not properly accounted for. Perhaps the redshift measurements themselves were systematically biased, placing galaxies closer than they actually appeared. Perhaps there were selection effects in how Webb chose its targets, preferentially finding the most extreme examples. Each of these possibilities received serious investigation, but as follow-up observations proceeded, many of the initial findings were confirmed. Spectroscopic measurements verified the redshifts of numerous candidates. Detailed modeling ruled out simple explanations based on dust or lensing. The galaxies were real, they were as distant as they appeared, and they presented a genuine puzzle. These observations present cosmologists with an uncomfortable question. How do you build massive, mature galaxies in a universe barely old enough to form its first stars? Building a galaxy isn't instantaneous. It's a process governed by physical laws that impose strict limits on how quickly things can happen. You can't simply wish stars into existence or assemble a galaxy overnight. Every step requires time. And when we calculate how much time each step should take, we arrive at timescales that seem incompatible with what Webb is observing. Start with the most basic requirement: gathering the raw material. Galaxies form inside halos of dark matter, invisible scaffolding that provides the gravitational wells where ordinary matter can collect. After the Big Bang, dark matter began clumping together under its own gravity, but this process isn't instantaneous. Density fluctuations need time to grow. Computer simulations show that dark matter halos, massive enough to host substantial galaxies, don't form until several 100 million years after the Big Bang at the earliest. This sets a fundamental timeline. You can't build a galaxy before you have the dark matter structure to support it. Once a dark matter halo exists, ordinary matter, mostly hydrogen and helium gas, begins falling into it. But this gas is hot, heated by the violence of the Big Bang and by shocks as it falls into the gravitational well. Hot gas doesn't collapse easily. It has too much internal pressure. The gas must cool before it can condense into stars. Cooling happens when atoms collide and emit radiation, carrying energy away. But in the early universe, with only hydrogen and helium available, cooling is inefficient. These elements don't radiate energy easily at the temperatures and densities involved. The gas cools slowly, taking tens of millions of years to reach temperatures low enough for gravitational collapse to overcome thermal pressure. Now the gas can collapse. Gravity pulls it together into denser and denser clouds. But even this process takes time. The timescale for gravitational collapse depends on density. Dense regions collapse faster, but even in relatively dense environments, collapse takes millions of years. As the cloud contracts, it fragments into smaller pieces, each collapsing independently. Eventually, some of these fragments become dense and hot enough at their cores for nuclear fusion to ignite. A star is born, but forming a single star doesn't make a galaxy. You need millions or billions of stars. Each star formation event converts only a small fraction of the available gas into stars. The rest is blown away by stellar winds, radiation pressure, and eventually supernova explosions. The efficiency of star formation is low, typically just a few percent of the available gas per unit time. Building up a large stellar population requires sustained star formation over extended periods, not just a brief burst. Then there's the question of stellar lifetimes. The first stars in the universe, called population 3 stars, were probably very massive, perhaps tens or even hundreds of times the mass of our Sun. Massive stars burn their fuel quickly. A star 100 times the Sun's mass might live only a few million years before exhausting its nuclear fuel and exploding as a supernova. This is important because the heavy elements Webb is detecting in early galaxies, elements like carbon, oxygen, and iron, can only be created inside stars and released through supernova explosions. To build up measurable quantities of heavy elements, you need multiple generations of stars. The first generation forms from pure hydrogen and helium, lives out its short life, and dies in supernovae that scatter newly synthesized elements into the surrounding gas. This enriched gas cools and collapses again, forming a second generation of stars with slightly higher heavy element content. These stars also live and die, further enriching the gas. After several cycles, the heavy element content becomes significant enough to detect in spectroscopic observations. Each cycle takes time. Even with very massive, short-lived stars, you're looking at millions of years per generation. Multiple generations mean tens of millions of years, possibly more than 100 million years, just to achieve the metallicity levels observed in some of Webb's high redshift galaxies. And this is under optimistic assumptions. If the early stars weren't all extremely massive, if some were longer-lived, the timescales stretch even further. Structure formation adds another layer of complexity. The organized disks and spiral arms seen in some early Webb galaxies don't appear spontaneously. They form through angular momentum, conservation as gas collapses into a rotating disk, and through gravitational instabilities that create spiral density waves. These processes require the galaxy to settle into a stable configuration, with stars and gas moving in organized orbits rather than random chaotic motion. Simulations suggest this settling process takes hundreds of millions of years, sometimes approaching 1 billion years, for well-defined spiral structure to emerge. When you add up all these timescales, the problem becomes clear. Dark matter halo formation, a few 100 million years. Gas cooling and collapse, tens of millions of years. Multiple generations of star formation and heavy element enrichment, at least 100 million years, probably more. Structural organization, several 100 million years. The total timeline, even under the most optimistic assumptions, pushes close to or exceeds 1 billion years. Yet Webb is finding galaxies with all these characteristics existing just 300 to 400 million years after the Big Bang. There's no way to simply speed up these processes without breaking known physics. You can't make gravity work faster. You can't make gas cool instantaneously. You can't make stars burn through their nuclear fuel at arbitrary rates. Nuclear fusion operates at rates determined by quantum mechanics and the strong nuclear force. These aren't adjustable parameters, they're fundamental constants of nature. Some researchers suggested that perhaps early star formation was more efficient than we thought. Maybe instead of converting just a few percent of available gas into stars, the early universe managed 10 or 20% efficiency. This would allow more stars to form more quickly. But even doubling or tripling star formation efficiency doesn't solve the fundamental problem. You still need multiple stellar generations for heavy element enrichment. You still need time for structures to organize. Higher efficiency helps, but it doesn't compress the timeline enough to explain what Webb is seeing. Others propose that the first stars were even more massive than we assumed, perhaps reaching hundreds or even thousands of solar masses. These supermassive stars would live incredibly short lives, just a few million years or less, and produce enormous amounts of heavy elements when they died. This could accelerate the enrichment process, but supermassive stars also have problems. They're theoretically unstable, likely to blow themselves apart before completing their life cycle. And even if they existed, they don't solve the structural organization problem. Building an organized disk galaxy still requires time, regardless of how quickly you enrich the gas with heavy elements. There's also the question of sheer numbers. Even if you could explain one or two anomalously massive early galaxies through some special circumstance, Webb is finding many of them. Statistical arguments become important. If massive galaxies at high redshift were extremely rare, requiring special conditions, you wouldn't expect to find multiple examples in the relatively small areas Webb has observed so far. The frequency of these objects suggests that whatever process is forming them is not a rare exception. It's a normal part of early galaxy evolution, and that's what existing models can't accommodate. The cosmological simulations that have been refined over decades, that successfully reproduce the observed properties of galaxies in the modern universe, simply don't produce massive, structured galaxies at redshifts above 10 or 12. You can adjust parameters within reasonable ranges. You can tweak assumptions about star formation efficiency or dark matter properties. But there's no straightforward way to make the simulations match what Webb is observing without fundamentally changing something about our understanding of the early universe. Faced with this impossible timeline, scientists have proposed various explanations, some requiring tweaks to theory, others demanding we rethink fundamental assumptions. When observations don't match predictions, scientists respond by questioning their assumptions. The simplest explanations address potential measurement errors. Perhaps the galaxies aren't as distant, massive, or mature as they appear. Perhaps some systematic bias in how we interpret the data is leading us astray. This conservative approach looks for ways to preserve existing theory by identifying mistakes in observation or analysis. Redshift measurements, for instance, can be tricky. Most of Webb's initial high redshift galaxy candidates were identified using photometry, measuring the brightness of an object through different filters. By comparing how bright a galaxy appears at different wavelengths, astronomers can estimate its redshift. But this method can be fooled. Certain types of galaxies have unusual spectral features that can mimic the signature of extreme distance. A moderately distant galaxy with strong emission lines might produce a photometric signature similar to a much more distant galaxy without those lines. The solution is spectroscopy, spreading the galaxy's light into a detailed spectrum that reveals individual absorption and emission features. Spectroscopic redshifts are much more reliable than photometric estimates. As follow-up spectroscopy has been obtained for many of Webb's candidates, some have indeed been revealed as closer than initially thought. The photometric estimates were misleading. These cases get reclassified, removed from the list of problematic early galaxies, and the tension with theory diminishes slightly. But spectroscopy has also confirmed many of the extreme candidates. Galaxies initially estimated at redshift 13 or 14 have had those distances verified through detailed spectral analysis. The objects are real. They are as distant as they appeared. The problem remains. Another conservative explanation involves dust. Cosmic dust absorbs and scatters light, and it does so differently at different wavelengths. Dust can make a galaxy appear redder than it actually is, potentially mimicking the effect of cosmological redshift. It can also obscure some of the galaxy's light while allowing other wavelengths through, potentially leading to incorrect mass estimates. If early galaxies contained more dust than expected, or if the dust had unusual properties different from dust in the modern universe, it might explain some of the observations. Detailed modeling has explored this possibility. In some cases, dust does appear to be affecting the observations, making galaxies seem slightly more massive or more evolved than they are. But dust alone can't explain all the anomalies. Some of the high redshift galaxies show characteristics that are difficult to attribute to dust effects. And there's a chicken and egg problem with dust itself. Dust is made of heavy elements created in stars. If you're seeing significant amounts of dust in an early galaxy, that's evidence of substantial prior star formation, which brings you back to the original timeline problem. Moving beyond measurement errors, some explanations propose that star formation in the early universe was simply more efficient than current models assume. Perhaps the conversion of gas into stars happened faster, or with higher efficiency, than what we observe in nearby galaxies. The first generation of stars might have been predominantly very massive, burning quickly and producing heavy elements rapidly. If you could pack more star formation into less time, you might be able to build massive galaxies faster than standard models predict. There's some theoretical support for this idea. The early universe was denser, hotter, and had different chemical composition than the universe today. These conditions might favor the formation of massive stars. Population 3 stars, formed from pure hydrogen and helium, might naturally skew toward higher masses than later stellar generations. If this is true, the first burst of star formation could have been extraordinarily intense, creating large stellar populations quickly. But there are limits to how much this helps. Even very massive stars take time to form, and they still need to go through their full life cycle to enrich the surrounding gas with heavy elements. You can compress the timeline somewhat, but you can't eliminate the fundamental constraints imposed by stellar physics. And more efficient star formation creates its own problems. If you form stars too efficiently, you consume all your available gas too quickly, leaving nothing for future generations. You end up with a galaxy that stops forming stars very early, which doesn't match what we observe. Another class of explanations involves dark matter. Standard cosmological models assume dark matter is cold, meaning it consists of heavy particles moving relatively slowly. Cold dark matter clumps together efficiently, forming the halos that host galaxies. But some physicists have proposed that dark matter might be warm, consisting of lighter particles moving at higher speeds. Warm dark matter doesn't clump as efficiently on small scales. This changes the timeline of structure formation in subtle but potentially important ways. If dark matter is slightly warmer than assumed, or if it has other non-standard properties, it might allow dark matter halos to form earlier or grow faster than cold, dark matter models predict. This could provide the scaffolding for early galaxy formation sooner than current simulations suggest. Some models incorporating modified dark matter properties do produce earlier galaxy formation, potentially easing the tension with Webb's observations. The challenge is that warm, dark matter makes other predictions that don't match observations. It suppresses the formation of small galaxies, for instance, predicting fewer dwarf galaxies than we actually observe in the local universe. Finding a dark matter model that allows earlier massive galaxy formation while still matching all the other constraints from galactic structure, cosmic microwave background observations, and large-scale structure is difficult. It requires very specific properties, fine-tuned in ways that seem contrived. More radical proposals question the framework of general relativity itself. Modified gravity theories, variants of what's called MOND, or modified Newtonian dynamics, suggest that gravity behaves differently on large scales than Einstein's equations predict. These theories were originally developed to explain galactic rotation curves without invoking dark matter. In MOND-type theories, galaxies hold together through modified gravitational attraction, rather than through the gravitational pull of invisible dark matter halos. Some versions of modified gravity allow structure to form earlier in cosmic history. Without the need for dark matter halos to form first, ordinary matter might be able to collapse into galaxies more quickly. This could potentially explain how Webb is seeing mature galaxies so early. The problem is that modified gravity theories struggle to explain many other observations. They have difficulty accounting for galaxy cluster dynamics, gravitational lensing observations, and especially the cosmic microwave background's detailed properties. Most cosmologists consider these theories incompatible with the full range of observational evidence. Perhaps the most radical proposal is that the Big Bang timeline itself is wrong. If the universe is older than 13.8 billion years, then there's more time for early galaxies to form and mature. A universe that's, say, 15 or 16 billion years old would give an extra billion or 2 billion years for structure formation, potentially resolving the tension with Webb's observations. The difficulty is that the age of the universe isn't determined by a single measurement. It comes from multiple independent lines of evidence that all converge on the same answer. The cosmic microwave background provides one measurement. The expansion rate of the universe today, combined with observations of distant supernovae, provides another. The ages of the oldest star clusters provide a lower limit. The abundances of light elements created in the first few minutes after the Big Bang provide additional constraints. All of these point to an age very close to 13 of t.8 billion years. Changing the age significantly would require explaining why all these different measurements are systematically wrong in coordinated ways. Some researchers have suggested that perhaps our understanding of the early expansion history is incomplete. Maybe the universe expanded differently in its first few 100 million years than we assume. Maybe there were phases of accelerated or decelerated expansion not accounted for in standard models. These modifications could change the relationship between redshift and cosmic time, potentially giving more time for early galaxy formation than we think. But such modifications would need to be compatible with cosmic microwave background observations, which constrain the early expansion history quite tightly. What's becoming clear is that no single, simple fix resolves all the issues. Some combination of factors is likely at work. Perhaps star formation was somewhat more efficient early on. Perhaps dark matter properties are slightly different than assumed. Perhaps there are selection effects in which galaxies Webb detects, or systematic uncertainties in mass estimates that we haven't fully accounted for. The truth might involve multiple small corrections rather than one dramatic revision. As astronomers continue gathering data, a deeper question emerges, not just about these specific galaxies, but about what it means when the universe surprises us. Science progresses through surprises. The moments when observations deviate from predictions are often the moments when we learn the most. History is filled with examples of anomalies that seemed like problems at first, but ultimately led to deeper understanding. The orbit of Mercury didn't quite match Newtonian predictions, and that discrepancy eventually pointed toward general relativity. The rotation curves of galaxies didn't match expectations based on visible matter, and that led to the discovery of dark matter. Unexpected observations aren't failures of science. They're invitations to refine our models, to question our assumptions, to look more carefully at what we thought we understood. The James Webb Space Telescope is still early in its mission. It launched just a few years ago, and its planned operational lifetime extends for many years as our moves into the future. The observations causing tension with Big Bang timelines come from a small fraction of the data Webb will ultimately collect. As the telescope continues surveying the sky, observing more galaxies at different distances and in different environments, the picture will become clearer. Patterns that seem significant now might dissolve with larger sample sizes, or they might strengthen, forcing more substantial revisions to theory. Other observatories are contributing complementary data. The Atacama Large Millimeter Array, a network of radio telescopes in Chile, can observe cold gas and dust in distant galaxies, providing information about star formation rates and galactic structure that Webb's infrared observations don't capture directly. Ground-based telescopes with adaptive optics can obtain detailed spectra of high redshift galaxies, verifying distances and measuring chemical compositions with high precision. X-ray observatories can detect supermassive black holes in early galaxies, offering clues about how these enormous objects formed and grew. Each observatory sees a different aspect of the same galaxies, and combining these perspectives gives a more complete picture. Upcoming spectroscopic surveys will be particularly valuable. Spectroscopy takes longer than photometry, so initial discoveries often rely on quick photometric measurements that can be ambiguous. Dedicated spectroscopic follow-up campaigns are now underway, obtaining detailed spectra for dozens of high redshift galaxy candidates. These observations will determine masses more accurately, measure star formation rates more reliably, and identify the presence of heavy elements with greater certainty. Some galaxies will turn out to be less extreme than initial estimates suggested. Others will have their unusual properties confirmed. The statistical distribution of galaxies at different epochs will become clearer. New instruments are already being planned. Future space telescopes will build on Webb's capabilities, potentially offering even greater sensitivity or covering different wavelength ranges. Ground-based extremely large telescopes, with mirrors 30 meters across or larger, will have the resolution to study internal structures of high redshift galaxies in detail. These next-generation facilities will push observations even deeper into cosmic history, potentially reaching the very first generation of stars. Each new instrument brings the possibility of new surprises, new tensions between observation and theory, new opportunities for discovery. The current tension between Webb's observations and Big Bang timelines might resolve in several ways. It's possible that as we gather more data and refine our analysis techniques, the extreme properties of early galaxies will seem less extreme. Systematic uncertainties might be identified and corrected. The galaxies might turn out to be more consistent with existing models than initial observations suggested. This would be a satisfying resolution in some ways, confirming our theoretical framework and demonstrating the importance of careful measurement. Alternatively, the tension might deepen. More observations might reveal that massive, Structured galaxies in the early universe are even more common than currently thought. The conflict with theoretical predictions might become impossible to ignore, forcing genuine revisions to our understanding of galaxy formation, dark matter, or even the expansion history of the universe. This would be scientifically exciting, opening new questions and new research directions, even as it unsettles established ideas. Either outcome is valuable. Science doesn't require that our theories be perfect or that our predictions always match observations. It requires that we remain honest about what we observe and willing to revise our understanding when evidence demands it. The models we use to describe galaxy formation, cosmic expansion, and the evolution of structure are tools, not truths. They're frameworks we've built to make sense of observations, to organize data into coherent narratives. When new observations don't fit the framework, we don't discard the observations. We refine the framework. There's a certain humility required in cosmic investigation. The universe doesn't owe us comprehensibility. It doesn't arrange itself for our convenience or organize itself to match our expectations. We're trying to understand phenomena that occur on scales of billions of light years, over timescales of billions of years, involving physical conditions we can never directly experience. We're limited to observing photons that have traveled across the universe, piecing together cosmic history from these faint signals. It's remarkable that we can do this at all, that we can construct coherent models of the universe's origin and evolution. But we shouldn't be surprised when those models need adjustment. The galaxies Webb is observing existed more than 13 billion years ago. We're seeing them as they were when the universe was young, when the first stars were igniting, when the cosmic web was just beginning to take shape. These galaxies no longer exist in the form we're observing. They've merged with other galaxies, evolved, changed beyond recognition. Some of them might be part of much larger systems now, their stars scattered among the hundreds of billions that make up mature galaxies like the Milky Way. We're glimpsing a phase of cosmic evolution that was brief and transitional, a moment in the universe's long history. Our own existence is connected to these ancient processes. The atoms in our bodies were forged in stars, scattered through space in supernova explosions, incorporated into later generations of stars and planets. The carbon in our cells, the oxygen we breathe, the calcium in our bones, all of it was created through nuclear fusion in stellar cores billions of years ago. Some of those atoms might have been part of the early galaxies Webb is now observing. We are, quite literally, made of material that has cycled through multiple generations of cosmic evolution. This connection between human existence and cosmic history gives a certain weight to astronomical observations. We're not dispassionate observers studying an abstract subject. We're part of what we're studying. Understanding how galaxies formed in the early universe is, in a sense, understanding our own origins. The processes that built those first galaxies, whatever they were, eventually led to the formation of our galaxy, our solar system, our planet, and us. The mystery of early galaxy formation is part of the larger mystery of how the universe became capable of producing conscious beings who could look back and wonder about their origins. There's a privilege in living during an era when we can ask these questions. For most of human history, the nature of galaxies, the age of the universe, the process of cosmic evolution, all of it was completely unknown. We knew stars existed. We could see the Milky Way stretching across the night sky. But we didn't know it was a galaxy, didn't know there were billions of other galaxies beyond it, didn't know the universe had a beginning or that we could trace cosmic history back to that beginning. We've learned all of this within the last century, an eye blink in human history. And we're still learning, still refining, still discovering. The tension between Webb's observations and theoretical predictions is part of that ongoing process. It's a reminder that our understanding is incomplete, that the universe still holds surprises, that there's still wonder to be found in looking up at the night sky. On a clear night, far from city lights, you can see a few thousand stars, ancient light arriving at your eyes after journeys of years or centuries. But you can't see the distant galaxies, the ones Webb observes, the ones that have cosmologists puzzled. Their light is too faint, too redshifted, too far beyond what human eyes can detect. You need instruments to see them, telescopes, detectors, years of engineering and planning and observation, yet those photons are arriving nonetheless. Light from galaxies that existed when the universe was young, traveling for more than 13 billion years, crossing incomprehensible distances, finally reaching Earth and entering our telescopes. That light carries information, stories encoded in wavelengths and intensities, stories about how those galaxies formed, what they were made of, how they evolved. Stories our theories can't yet fully explain, and perhaps that's exactly as it should be. The joy of science isn't in having all the answers, it's in the search itself, in the process of questioning and observing and refining our understanding. The cosmos doesn't reveal its secrets easily, and maybe that's what makes them worth pursuing. The universe remains mysterious, surprising us even when we think we've figured something out. And in that mystery, in that capacity to still astonish us after all we've learned, lies a kind of grace. We stand under the night sky, small and temporary, looking up at light from the edge of time. We build instruments to see further, to look deeper, to understand more. Sometimes what we find matches our expectations. Sometimes it doesn't. Either way, we keep looking, keep wondering, keep reaching out toward the stars, trying to understand the cosmos that gave rise to us, trying to trace our origins back through billions of years of cosmic history. The light keeps arriving, the questions keep multiplying, and we keep searching for answers, knowing that each answer will likely bring new questions, new mysteries, new reasons to look up in wonder at the universe we call home.